The big point of the previous video was this formula for what is the volume of the region that you get if you take the area under some graph and revolve it around the x-axis. And so this is what we call the disk method because the cross-sections look like disks. Well, now let's make this a little bit more interesting. Let's say that instead of just rotating the area under some function f of x around the x-axis, let's take two different functions, an f of x and a g of x, and let's say that we're going to take the region in between that and rotate it around. So now the 3D picture that we get, I maybe made this a little bit more complicated than I should have. But this is what's going on. If we were to take a look at this, so this is kind of like a side-on view, it's going to be, some kind of tube with a hole in it where the width of the outside of the tube, it varies. The width of the hole in the middle, it varies. But we think about it, if we take a typical cross-section of this up here, it looks like this. And what is the area of this? Well, there's two different radii that we have to consider here. So let's say that this is r sub out, and let's say this is r sub in. The area of this region is exactly going to be the area of the bigger circle, which is pi times r sub out squared. But then we have to subtract off the area of the inner circle, which is pi times r sub in squared. And so the area here is pi times the outer radius squared minus the, I already factored out that pi, so I can just write the inner radius squared. This is the area. This is the area of one of the cross sections. And so, once again, going back to our section 6.2 setup, to get volume, we integrate the area, the cross-section area, along a given interval. So what we're going to do here is that to come up with what is the volume that we get when we take the region between these two curves and revolve around the axis, we're going to be integrating this expression down here. So this shape, let me just draw it one more time. We have different colors here. So it's the region that is inside one circle, outside another circle. This is commonly called a washer. And so here is our big formula in this section. So if we have two functions, f and g, where f of x is always greater than or equal to g of x, and we assume everything's greater than or equal to 0, on this interval a to b, and the solid you get by rotating the region between the graphs of f and g around the x-axis, it has volume. Well, exactly, just integrate this from a to b. And so we factor out that factor of pi. But then, what's going on here? What is r sub out? What is r sub in? Those are just going to be f of x and g of x respectively. The outside radius is from here to here, that's f of x. The inside radius from here to here, that's g of x. So this is our big overall formula here. So this is what we have in this section, and this generalizes what's going on with the disk method. If we were to set r sub in to be 0, it would just be this here as a formula. It would just be integrating f of x squared, and that looks just like what we had before. Okay, so that's the big formula here. Let's go ahead and use the formula. So here is a problem to think about. So the region bounded by that handful of curves. Y is x squared plus 4, y is 2, x is 1, x is 3 is rotate about the x-axis. Let's draw a picture of what's going on. So x is 1 and x is 3. So there's two bounding things. Y is equal to 2. And y is x squared plus 4. And so that starts at 4 and goes up. And so this is the region that we are this is the region we are revolving around the axis. Okay, so our outer radius is going to be x squared plus 4. Our inner radius, let's label that. R sub out is x squared plus 4. R in is equal to 2. And so all we have to do is copy down this formula right here. So that's going to give us v is pi times integral from 1 to 3. So the outer radius squared, so x squared plus 4 squared, minus the inner radius squared, so minus 2 squared, integrate that with respect to x. Okay, so we can simplify this just a smidge. Integral from 1 to 3. So this becomes x to the 4th plus 8x squared plus 16 minus 4 is plus 12 dx. And then this is a pretty simple integral to do. I'm just going to write down the final answer. This ends up as 21/26 pi over 15. Okay, so let's recap of this video here. This is the big formula you need. If you're rotating the region that's trapped between two curves about the x-axis, this is the formula you want to go with. To conclude this video, let's have our first pre-class problem for section 6.3. So find the volume of solid you get by rotating the region bounded by those four curves about the x-axis. Should be very much just like the problem we just did.